Thank you, Cozy, for introducing. Hi, everyone. Thank you for having me today. It's very happy to present today here. Uh, Today, the topic is the Korea's project, which is a power grid monitoring based on Synchro-Waveform. So I'm going to explain about the wide area monitoring system, and then Synchro-Waveform technology, and then about the related blackout, and so why do we need this kind of monitoring, and then why the Korea government start this project. Uh, I'm going to briefly explain background motivation of the project research, and then followed by the project overview, and then its project's main technology and methodology, and finally conclusions. Okay, so wide area monitoring system, in short, WAMS, in power system. This WAMS is keep watching the voltage and currents and powers and reactive power in the wide area of the systems. So based on these measurements, is trying to see the situational awareness for the reliable grid operations. So the WAMS is first start with the real-time measurement, so which is done by the PMU and scalar. PMU is phasor measurement unit, and scalar is a supervisory control and their execution system. Historically, the data is captured, measured by the magnitude. I mean, the power system is AC system, so is the data or the voltage and current is sinusoidal data. Okay, so a long time ago, those data is captured by its magnitude, but however, is difficult to measure its angle. The AC waveform has the magnitude and phase angle. So that's why the PMU is introduced to measure the magnitude and phase angle as well, based on the GPS synchronized signals. Okay? So PMU and scalar is widely used measurement. Based on these measurements, the data processing layer performs state estimation and the real-time contingency analysis. It's kind of the analysis of the system. So state estimation is to provide the phase angle from based on the measurement and system model. But with the introduction of PMU, the state estimations, the accuracy is very becomes higher because the PMU itself can measure the phase angle in some places. But all places cannot be covered PMU. In some places, mostly covered by scalar. So state estimation is still required. And then based on that, the operator make decisions for some kind of visualization or the actions is required. And this is online. And then also when event, something like blackout or outage happens, the WAMS should analyze the event in after the event. It's called post-event analysis. So we need to playback, which is plays at the event moment. So event reconstruction and scenario replay should be done. So the WAMS provide these functions, and then to eventually to improve the grid reliability, and then detect the instability, finally prevent blackout. So I'm going to explain about why we do need the WAMS. It start with the blackout in the global. First, one of the well-known the blackout was the New York 2003 New York blackout. Is northeastern U.S. part is without power, and then 61 gigawatts the power loss, and then 55 million people without power. So at that time, the transmission line was tripped. Tripped means is disconnected because of any issues, something like the tree contact. So this event is happening in cascading. So, and then eventually great generator is tripped, and then voltage is becomes low, and then more generator trips, more line trips. This kind of cascading event eventually leading to this blackout. And so at the time, there's some the situational awareness issues, which it was that the state estimation is not working properly, and then analysis is not working properly. I'm not going to in detail about these things, but this kind of the low situational awareness is it affect the operators of the actions too late. So operators they didn't see the alarm properly. This kind of situation awareness could be prevent the further blackout, but at that time it was not good. Okay, and the lessons learned from this blackout is that the voltage stability issues, and then the other thing is this situational awareness requirement. So they try to implement deploy the PMUs to improve the accuracy of the state estimation and then faster situation awareness during fault conditions. So as I said, phasor PMU can measure phasor, including phase angles in AC system. So it's quite the faster measurements than scalar. And 2013, the California is blackout occurred, and 12 hours, 2.7 million people without power. The event is also very similar to the New York case. Is a transmission line is tripped, failure. After that, another transmission line overloaded. Then the generator is out, and then followed by cascading outage leading to the blackout. So it had also some kind of the situation awareness issues. At the time, it didn't the monitoring it was not monitoring the overload on the sub 100 kV equipment, which is this is 100 kV is kind of the boundary of transmission and distributions. So the system didn't see the distribution side. Okay. So the New York case is also the underscored the need to monitor the distribution side. So something like low voltage equipment below 100 kV. So recently, you might see the newspaper that blackout happens in the Spain and in Iberia is 12 hours, and then 56 million people without power. So this is the event first start from the events in the Europe, and then in the Spain, the generator is tripped out of service, and then followed by isolation of the Spanish grid from the other European grid. So, and then after cascading events, the whole system is collapsed. So there are many the root cause for the blackout, but is this there are some differences if this blackout from previous two cases. In this case, there are so many renewable energy resources, RES generation at that time. So I think I heard that it is more than 50%, 50 or 60% of renewable energy generations of total generation. So this kind of RES is very small scale generations. So many small scale PV or wind generations consists of comprise the RES. So it's difficult to see how much generations lost or where the generation is lost was not fully wearable or aware. Because so first event analysis, it has also faced the limitations, this kind of the lack of the situational awareness. Because the RES, small scale RES, is located in the distribution system, and then it's typically difficult to install the measurement units before near the small scale RES. So that's why in the entire system, difficult to see monitor this kind of the RES in detail. Okay, so from this event, we can learn that we need some kind of advanced stability monitoring, especially in the RES integrated grids, high penetration of RES system. So all these things lack the situation awareness, but it's not actual root cause. Actually, I think at the time the grid is very weak, very unstable situations, and then some single contingency, single outage triggers cascading events, and then finally leading to a major blackout. But if we have more situation awareness, then we can probably prevent this kind of the blackout. So we need a situation awareness to prevent this kind of fault and then blackout. So recently we have our grid, our power system has a lot of the RES, which is based on inverters, power electronic based devices. So it's more and more difficult to detect instability and also conduct the post-event analysis. So one of the most recent issues due to the high penetration of the RES is oscillations. So if you see here figure, there are many events happening the oscillations. The corresponding oscillation frequency is here. You can see from 854 to up to 80 hertz. So many wide range of the oscillations occurred. Okay, so in the involved devices is you see that the power electronic debate the power electronics based devices such as the wind turbine, and then the PV power plant, solar power plant, and another systems. So this kind of this DC based devices involve this kind of oscillations. So in major oscillation events in 2015 China, there's some interaction between this wind turbine and then the conventional generation systems. There's a interaction between two systems generating the 30 hertz oscillations. Because of these oscillations, the generators this side is tripped. Therefore, this long transmission, long power delivery through this HV DC, high voltage DC transmissions is reduced. Okay? And then, like in 2019 UK, there's a lightning induced the transmission fault, and then generate 9 Hertz oscillations with farm trip, eventually leading to 1.1 gigawatt blackout. So, in the all in all, the oscillation instability can trigger large-scale blackout in the recent power systems. In a situation is the same as in Korea, we're going to have more and more ESS, energy storage system, HVDC, and then FACTS, or flexible AC transmission system. All these systems are based on DC technology. So the power electronics. So in Korea, we're gonna facing this kind of the increasing renewable penetration, and then new stability issues, but which is resonance, and converter-driven stability. Okay, so the IEEE recently emphasized new stability issues. Other than historical the stability issues, of which so new stability is resonance and converter-driven stability. So resonance means that some kind of interaction between converters and grid, or converters and other the devices. And converter-driven stability is induced, oscillation is induced from the converter main control logic and the weak or system side interactions. So in these two stability generate oscillations, its frequency is 5 to 50, or something. Sometimes is going up to 80s. So these kind of oscillations cannot be captured by the traditional measurement PMU or the scalar RTU, the remote terminal units. So next level WAMS based on the high resolution measurement device is required for advanced stability monitoring. So we again, the Korean project is trying to use WMU device, which is a next level high resolution measurement device. In other words, is called the Synchro-Waveform. So let's compare these three: RTU, PMU, WMU. Actually, the scalar data based on RTU is captured data for few seconds, one sample per few seconds, very slow. And then the magnitude is value is magnitude only. And the PMU case is more the faster, is this two samples per cycle. You know, the cycle is one cycle is 60 hertz in US as well. So the 16 times per second. Therefore, two samples per cycle means 120 samples per second. Okay? So, but it's still very low resolution to capture the high frequency oscillations. So wide area, the WMU is it can capture the maximum 256 samples per cycle. These are maximum values. Actually, here you might see the reporting rate with the time tagging here, which means that any device can capture like WMU, but the thing is that we need to time tagging for each measurement, and then send this data to upper layer, the measurement monitoring system in the central location. So there is a challenge of the WMU utilizations. So I said here reporting rate with time tagging is Okay, so why do important to use WMU is that here you can see the actual waveform here. There's some glitch here. After with the PMU, this waveform is changing to the phasor data, and then the collect is sent to the upper layer monitoring system. This phasor can be used to reconstruct the waveform here. Then this PMU cannot see these glitches here, but WMU can see this kind of the glitch or the high harmonics features here. Okay, so high frequency oscillation monitoring is required in this kind of WMU device. Okay. So let's talk about the project overview. The title is Development of Stably Monitoring Technology for Expanding these power systems. So it's going to be 4 years. It just started, and then the budget is 8.8 million USD, and then there are 10 organizations involved in these projects. Sorry for Koreans, but many the industries, universities, and then public sector, and then are involved with this project. Okay, so in this, we're trying to develop the WMU based the WAMS, next level WAMS. So the left side is the previous conventional WAMS system based on PMU and SCADA. And then we're gonna develop some kind of the WMU based. WMU is generating so many data. It issues so many data, and then is a challenge to handle this kind of data, and how we need to handle the communication burden. So it's big challenge to develop this kind of the WAMS. So we have to make the monitoring scheme, monitoring architecture in the hierarchical. So we do some regional monitoring systems, and then it collects data from this WMU, any other the PMU and SCADA data, and then in this regional area, it performs the analysis, and then the result analysis is delivered to the upper layer, the central control center, the EMS. EMS is energy management system. Is controls all generations in the country. Okay? Okay, so we have the based on this architecture, we're gonna develop the WMU WDC prototypes and then related standards. Actually, PMU, I'm sorry, WDC. I didn't explain the WDC. WDC stands for Waveform Data Concentrator. So it collects data from the WMU or the PMUs and then store the data, and then they perform analysis based on data. So we're gonna develop the WMU and WDC, and then there's no standard for these two devices, so we need to develop also standards as well. And then based on these devices, we have to develop the online monitoring systems, which is hardware and then software is trying to stability monitoring and then any other the stage mediation and playback. And then finally, we're gonna implement the situational awareness technology. Is kind of the application part to, we're gonna build the real-time oscillation detection and localizations. So we need to detect the oscillation, and also we need to find out which device issues these oscillations, which is called localizations. And then in stability monitoring in DC intensive area with HVDC, FEX, ESS, and so on. and then also the converter stabilities. And then also we have to handle big data. We're going to use AI for this. Okay, so this is the software, and then this is hardware. This is the monitoring systems. This kind of development will be demonstrated in the actual field in another project. So before going to the field test, we need to do the validate the system using real-time simulator. Real-time simulator is mimicked power systems in the high functional devices. So which is called Hills-based validation. Hills stands for the hardware in the loop system, hardware in the loop simulation. Before going to field test, we need to conduct this kind of Hills-based the validations. So we're gonna test all the devices and then systems, and the algorithm is validated by this the real-time simulator. Okay, so there are 4 parts will be developed. First, number 1 is the device standard development, and then system development, and then validation 3, and then the algorithm development for number 4. Okay, so number 1 is the WMU, WDC development, and then the relevant standard should be defined. Okay, so WMU, waveform measurement units. There's also the commercialized devices in the several countries, including US. But we're gonna develop our own the devices. So actually, the localized sampling of this measurement is already implemented in the many relays or measurement units. But the thing is that we have to the time tagging from GPS clocks, and then send this data to upper layer monitoring systems with high speed communication infra. So it's very important, high speed HDC conversion, precise time synchronizations, and then storage, and then communication. This is challenge we need to address. And then WDC is also communicate with the WMU, and then upper layer the EMS, and also it has to handle the large amount of data in storage, and then it also provides high speed the communication between the WMU and EMS, and also it also should follow the communication standards. I'm sorry, this is typo 61A50. We're gonna follow the global standards, IEC 61A50, IEEE 37.180. Actually, these two the standards is for PMUs. But actually, this WMU, WDC standards is not developed yet. So we have to develop our own standards, and then if possible, if there be the global standardization of these units, we're gonna also want to involve the standardizations. Okay, it's about the standards. And then the second team is going to develop the online monitoring systems, and then WMU linkage technology and state estimation playback is a kind of the monitoring system development. So actually the WMU is they generate high volume of data, and then it make the communication burdens a lot So we cannot install everywhere the WMU. So we have to optimally place this WMU in several locations. Okay, so this time we need to figure out where we need to install the WMU for efficient monitoring systems, and also design specs of this WMU should be defined. And also in actual the monitoring system is developed, should be developed. So here we have this in the substation, there's going to be PMU, WMUs, and then we're going to install WDC in the substation, collect this data, and then in upper layer in the regional control center, there's going to be some super WDC or some kind of a WDC, but it collects data from several WDCs. Okay, so is in this super WDC, we're going to develop the local EMS and then linking these two in the regional piece, and then so this EMS will implement the algorithm for monitoring the applications. Okay, so so we're gonna develop this, state estimations, and then the time synchronism enables the distributed hybrid state estimation. And then after the event, we can use playback to see what happened at the moment, at the event. And then third one is validation through the real-time simulator. So we need to model the devices, DC devices, AC devices. And then this is the DC modeling, and then we need the power system modeling, AC bulk power system modeling, and then we need some kind of the reductions. Okay, and then finally, okay, so in this real-time simulator is mimicked actually the power systems, and then through amplifier it provides the voltage and current to the WMU and the PMUs. And then this device can provide measurement data to upper layer WDC through the communications. So this is the data communication part, and this is the physical connection part. Okay, so and then based on this WDC, local the EMS is performed. So we're gonna check this kind of the algorithms and those devices through this the real-time simulators. And finally, one of the important part is the development of the advanced online situational awareness. Okay? So this is key part of these whole systems. And first one is to detect the oscillations. Okay, we have many regions here, and then maybe some part generate oscillations. Okay, so the WMU at each location trying to monitor whether the oscillation happens or not. So it not only detect, it also figure out the direction of the oscillations. So based on the knowing the directions, we can find out the source location, oscillation source locations. So technically, we're going to use the DEF energy flow method, but I'm going to skip this part. But if we use WMU data, then we can compute more detailed this kind of the directions and source locations. And then we're gonna also the developed the algorithm for stability monitoring for DC device intensive areas. So as I said, we have many HVDCs in South Korea, and we have the MTDCs, and then HVDCs, and then there are many ESSs here. So in highly the intensive area, we have to the we need to have this situational awareness for these devices. So what kind so WMU based monitoring and awareness calculations, and then what kind of stability indexes we need to monitor these systems. So it's focused on the DC intensive area. And third one is converter side. We're gonna have many converter devices, usually RES. RES is based on inverter. So in this converter systems, we're gonna use WM data to align the impedance estimation followed by the stability monitoring. So this stability, unstable monitoring should be done in as soon as possible. So, okay, so we're going to develop. Final one is the AI and big data based the monitoring systems. We're going to have so many data from collected from the WMU, and then with another the data like the weather data, then we can the forecast the events, and then we can the prevent the future disturbance or future the event, and then after even event happens, we can perform the AI based post disturbance post event the analysis. Okay, here. Finally, in this project, we're gonna develop the next level, the WAMs, based on WMU. So first, we're gonna develop the WMU WDC for high frequency oscillations measurement. And then also we're gonna develop the situational awareness technology algorithms for detecting this kind of the instabilities, and then developing the online monitoring system with the hybrid SE and playback, and then finally the validations. Okay, so with this development WAMs based on WMU, we're gonna eventually trying to integrate the central EMS. And then also it can be used for the advanced analysis for this grid or for the new stability issues. So finally, this is conclusion of my presentation. So with high penetration of the IBR, a high frequency oscillation will be generated. So PMU and legacy measurement like PMU and scalar cannot capture these high frequency oscillations. So we're gonna use the WMU, but still its advantages. We still have the many technical challenges such as the addressing large volume of data and communication burden and standard and so on. And finally, we're gonna develop this WM-based next level WAMs for key technical challenges, and then for teams. Okay, that's all I have today. If you have any question, I'm happy to answer the.
Thank you, Dr. Choi, for the very comprehensive presentation. If you have any questions, please use the chat window. Then, our speaker, Dr. Choi, can easily recognize it. But personally, I have kind of many questions. So interesting presentation, and also this is a very important the topic and then also the project for the rest of the countries. And you mentioned that so the optimal location is important because we cannot place WMU at all of the locations. It's almost impossible. So we have to figure out which location we should place. And another important task must be how many sensors do we need to properly capture the converter driven oscillations or resonance oscillations? And so do you have any like ballpark numbers how many WMUs we need to cover the all of the events in the Korean peninsula?
Yeah, it's very good question. Thank you. First of all, the optimal location of WMU is very important. Uh, Maybe we have to figure out which is the optimal location for installing the WMU. But I come up with the ideas that we need to install WMU near the DC devices such as HVDC or the any other the multi-terminal device or high penetration renewable energy penetration areas. So because that kind of area is very can be established issues, so we need to install this WMU there. And another good location is that the boundary between two jurisdictions. Yeah, for example, in case of the USA, there are many ISOs, so they trying to install the PMUs between boundaries of the ISOs. So like it can be also used the kind of the locations. And the second question is that how many WMU we require to capture the actually uh, in one and one spot that we need one WMU is okay. One, but it's highly very tricky. I mean, it's some kind of the depend. In this case, depending on what kind of the application we use, because some application requires the WMU installs the very important or very the sensitive areas, for example, generators or the HVDCs or the many DC intensive areas. But in that case, I think it's recommended to one measurement unit for one device. But for example, very critical area, uh, there is a very weak grid, weak conditions. We can install as much as as many as the WMUs in very each the buses or each the lines. Yeah, yeah,
Okay, yeah, thank
yeah.
you.
Mm.
So you told me that you have already installed lots of PMU measurements, PMU devices in South Korea. And if we place the WMU at the same location as PMU, in this case, this is kind of overlapped in the future. And then in this case, do you plan to, for example, stop using PMUs and then use WMU only for that location? Or you will use both PMUs and then WMU at the same time, at the same location? Which one do you pick in the future?
Yeah, it's good questions. Actually, PMU cannot capture the high frequency oscillations. So we need to install WMU if it needs to install that area, then we can have to install WMU. About regarding the overlapping, I think if already it has PMU, then we don't need to remove the PMU. when the WMU still, even though the WMU is the installed, because if we have more and more data, then the accuracy is increased, and then sometimes we need the PMU data. Is low, is lower resolution than WMU, but it can the data is very light. Okay, so sometimes the PMU data is also required.
Okay, yeah, but for example, if you use like a downsampling for WMU, we can achieve the same performance of PMU quite easily using the WMU, and there is no reason to use PMU anymore. Once we install WMU at the same location, so that was my question. But
Yeah.
of course, the redundancy is good.
Mm.
But if we have more sensors, and then if we get the different results, which one we should believe?
Yeah, right. So that's why we need the state estimation. Actually, state estimation is filtering the errors, and also the generate uh, extract the very accurate real time the data states from redundancies. So even though there are many redundancies, it can figure out the most of the accurate data from there. So more redundancy is good for the state estimation.
Oh, okay. Yeah, I understand that because in the US we have like hundreds of phasor measurement units, and then now we are thinking. Actually, we have already developed a kind of software to utilize the PMU measurements for state estimation. So the usual state estimation was done by like EMS SCADA. So as you showed in one of the slides, the reporting rate is like one sample per a few seconds.
Mm.
But we can also utilize the PMUs, like a high frequency sampling. Of course, that is not that high compared to the WMU. And so anyway, yeah, this is really important for sure. And then so the another like a subsequent question is that so the monitoring system is good for the grid operators. So the grid operators can realize the like a converter driven oscillations using the monitoring systems. And then of course the grid operators can take the corrective actions to how to say mitigate the oscillations later on. But if the human beings will do it, um, I think we do not need to detect or monitor the event so quickly because the human's action is not that fast. Probably it takes a minute or maybe a few minutes or several minutes to take the corrective action, right? Once we realize the converter driven oscillation at one of the wind farms, and then they will start probably reduce the power or disconnect the wind farm. So it takes a minute. We cannot do it right away. But another option is that so that the monitoring system will be used for the automatic control system or automatic protection systems. So in this case, the detection time is really important. So what is the expected, a kind of like the detection time for converter-driven oscillations in your monitoring system? Like within 10 seconds or within 1 minute? What is the, the targeted detection time in your monitoring system?
Yeah, thank you. It's good questions. Uh, Actually, the we many monitor worms it provides the automatic protection system. In other words is the RAS remediation schemes. So it is when fault happens, is automatically the take actions in a few milliseconds to prevent the transient instability issues or angle stability issues, it should be very fast, because if it's too late, the system is collapsed. So this kind of alias should pass. But here for that transient stability, angle stability, angular stability, that requires very fast detections, is in milliseconds. But however, in this recent stability, such as convol driven or the resonance stabilities, this thing is very slowly increasing. Yeah, so it doesn't need to be fast within milliseconds, but as soon as possible is better. But so I think maybe some it has more the room. It can be it should not be very fast, but I think it should be less than 1 second. It depends on how the oscillation growing. If it's growing very fast, it should detect very fast. In other words, all devices is the tripped. So,
Okay.
yeah.
So the major targeted events is a kind of like a growing oscillations,
Right,
right?
right.
Okay, yeah, that really makes sense. Okay. So I do not see any additional questions from audiences. So in this case, can I quickly share my slides? Not slides actually. So yeah, hopefully you can see my the website. So anyway, the Fox next webinar will be held next week, specifically on June the 16th. And we will invite a professor from UK, United Kingdom, to showcase the analysis of the converted wave oscillations. So the same as today's topic, but today's topic covers how we can monitor it. And then, so the next week, another speaker will cover how we will analyze the inverter-driven oscillations some ways. And then the flyer was already uploaded to the Artifact session website. So yeah, please stay tuned and then enjoy the rest of the day. And then also the Professor Choi, thank you so much for the nice presentation today. So
Okay.
keep in touch.
Okay. Thank you very much. Okay. Thank you for inviting me today. Okay.
Yeah.
Thank you.
Bye for now, everyone.
Bye bye.